All right, let's get started. So, welcome everybody to another SNAPP seminar. It's our pleasure this week to have Harsha Honnappa, who's an associate professor at Purdue School of Industrial Engineering. He's an expert in queuing and stochastic processes, and today he's going to tell us about something at the intersection of a stochastic process classic, point processes, and deep generative modeling. So please, Harsha, take it away.
Thank you, Ziv. And I'd also like to thank the organizers for the kind invitation to talk about this topic. So today I'm going to talk about deep generative modeling for learning multi-scale point processes. And so the topic of this talk sort of came out of a broader question of how do we learn sort of complicated stochastic models from data. So and I'd point out what I mean by a complicated model, and it of course depends on the specific situation. But typically, in applied probability, we have very sharp insights into, a whole range of stochastic models. And the sharp insights generally come from our ability to analyze these models under certain assumptions. And these assumptions typically are around stationarity, ergodicity, and so on. The real world, of course, is way more messier than that. So when you collect data, you end up with uh, sampling or instrumenting systems that are much more complicated, and then you have to learn more complicated models. And so that was sort of the starting point for thinking about this problem. And this is joint work with my student, Shinlong Du, at Purdue. But it's also based on some work that was done in the past, but now we've sort of reached a point where we feel confident enough to write a full-blown paper about this. So for those of you who don't know who I am, I thought I'd just put together one slide that just sort of highlights what the Stochastic Systems Lab does at Purdue. So I direct quote unquote this lab. I always joke that I have undergrads who come to my office saying, "Hey, I want to see your lab." And then I'm like, "Well, you're in it. It's this table and this piece of paper here." So, but in any case, my interests are, essentially in mathematical methodology to understand stochastic systems across a range of different issues, including the analysis of stochastic systems, design and control, and model estimation or inverse problems. And today's talk sort of falls into this last bucket. Okay, with that out of the way, let me talk about a sort of stochastic modeling pipeline, but in a data-driven setting. So I want you to think about a service system, for example, it could be like a call center or a hospital or something, where you have flows of patients or calls going through a really complicated system, and these calls are coming in over time, and there are the arrival rate of calls is changing with time. You can also think of like a logistics or manufacturing system where there are lots of complicated flows, reentrant flows, and so on, or a shared transportation system where demand and supply is changing not only temporally but also spatially through a geographical region. And one interesting application that I've started to get into is like space operations, where again you see really complicated interactions in these systems. So a significant recent sort of innovation, if you like, in these types of industries is our ability to instrument these systems and collect data about the state of these systems, whatever state means. And one of the reasons why you'd want to do this is to create like a digital twin that you can sort of use to gain insight into a system almost in real time, but also to control it in real time. And this leads to the following pipeline. So you would collect data that's typically in the form of point processes that are temporally ordered. And these point processes are fluctuating at different spatiotemporal scales. This data is typically stored in a data set in a database from which you can do feature selection. And this feature selection is used to estimate a model of what we are seeing in the data. And this model is eventually used in some downstream task, which could be some form of performance prediction, for instance, or maybe design or control. And I would broadly put this into a large bucket of that I would call as inference. And this talk is essentially focused on the middle task, namely model estimation. And I want to look at how do we estimate models of stochastic systems whose states are varying or fluctuating in complicated ways, in multiple scales. So to give you an idea on what type of a system I'm thinking about and what kind of models we might focus on, let me paint a picture by using two vignettes. And the first one relates to transportation, and then we'll see like the specific one that I want to focus on in this talk. So uh, think of a transportation network in a city. So the demand and supply in this network is sort of changing spatio-temporally over this geographical region. So in a paper that I wrote a few years ago with a colleague in civil engineering, so Satish Ukasuri is a distinguished professor here at Purdue in civil engineering, and Wenbo Zhang was his former PhD student. So they had a question of, okay, suppose that you had, like an app-based taxi service like Uber or Lyft operating in conjunction with a sort of traditional taxi service, like a yellow cab service in Manhattan, then what kind of congestive effects would you see? So if you want to answer this congestion question, you really want to use like a queuing network. And when you look at this system, it's not clear what queuing network you should use a priori. So you look at the data, and what we sort of concluded was that, okay, at some spatial scale, we can sort of locally model the interactions between passengers who are flowing in and the vehicles that are flowing in to satisfy this passenger demand through essentially some kind of a localized Jackson network. And then we also included like a road network model, which was an MMCQ. Um, and, we sort of tried to fit this model at different geographical scalings and across the city. And what we found was, it was very hard to actually fit this model to the available data. And secondly, the best fits that we were able to make were only very, very localized. We were never able to, both in space and time. So we were never able to actually capture all the complexity that we were seeing in the data in a satisfactory way. And even if you just focus only on, inflow of passengers or vehicles, you will see that the reason why this is a hard problem is because there are fluctuations that are happening at multiple spatio-temporal scales. So if we just look at arrivals to one location in this network, then we already see multi-scale nature. So, but this is not a phenomena that's unique to transportation networks. So even if we look at, for example, call centers, this is data from this classic data set collected by Avi Mandelbaum, and I think it's now managed by Galit at the C Lab at Technion. So they have this large data set on calls that are being made to a large call center. And this is, so I just filtered out like a few Fridays from this data set. And what you immediately see is there's sort of a diurnal pattern to this, the call volume. And this is a call volume at like a 30-second time scale or something like that. So clear, time of day effect. But also there's like a sub-hour or even like sub 15-minute fluctuations that you can see in this data set. And so, it's not just at, these two time scales. Like you can look at these fluctuations emerging at, multiple time scales in this data set. And this is from a paper by Xiaowei Zhang, Jeff Hong, and Jiheng Zhang a few years ago, where they looked at the mean and the variance of the arrival counts at a 10-minute time scale. And again, it immediately stands out that the mean has a very clear diurnal effect, like it's varying with time. But you also see that the variance also changes. So the variance is this blue curve, and that's also changing, with the time of the day. But it's also, significantly different from the mean, which means that this data is being generated by a process that is not necessarily Poisson-like. And so there's more variation that's emerging at multiple timescales that's affecting these statistics. And this is a well-studied phenomena, and people have looked at this data set quite extensively. And one of the things that we do know from stochastic modeling is that the way to model this type of data is to use a mixture model, essentially an infinite component mixture model. So let me fix this idea a little bit, and let's say that X is our data sample path that we get from looking at, for example, the call center. So let's keep that call center example at the forefront. And let's say that there is some unknown data generating measure that produces these sample paths. And the data in this case will consist of multiple traces of point locations throughout time and space. And what we want to do is use a model. We want to model this data generating measure, which we don't know. And the way we will model it is through a mixture model of this form. Here, this mixing measure mu, in essence, captures the multi-scale structure of the point process. This P is some point process kernel that is either given to us or has to be learned. And in general, what we'll see is that this measure, this model, is not going to be equal to this data generating measure. It's a model. But also, this underlying multi-scale structure variable, this lambda, is unobserved. And also it has continuous support, which means that what we have is like this infinite mixture model. And the canonical example that I want you to keep in mind of these types of models is a Cox process or a doubly stochastic Poisson process, where we specify that this kernel P of a given lambda here, so this thing is actually a Poisson kernel when conditioned on this process lambda. And also this measure mu, therefore, will be supported on some underlying space of right continuous functions that have jumps in them. So given this type of modeling setup, our problem now is to solve the following. So we want to estimate this infinite mixture model of these types of multi-scale point processes. And in this talk, I'm going to focus exclusively on what amounts to the doubly stochastic Poisson or Cox process. But the methodology I'm going to introduce is actually not tied to this assumption at all, but it helps to have that in mind. So here's the sort of outline of what's coming along in the next 40 minutes or so. So in the first part of the talk, I will introduce our methodology. And I will first go through a classic approach that, that's been studied extensively in the literature using some kind of time binning. But I'll also point out the problem with these time bin models. And then I'll introduce our methodology on using score matching and deep generative modeling to solve this estimation problem. And in fact, what we are trying to solve is something called as a nonparametric MLE, a nonparametric maximum likelihood estimation problem. And I'll then illustrate this methodology with a number of numerical examples. I think this is going to be the bulk of the talk. In fact, one of the things that we'll see is because we're trying to embrace this messiness of reality, probabilistic and statistical guarantees become much harder to provide. But I'll try to sketch some of the things that we have. And this is where the source of many of the open problems lie, which I will point out in the last section of the talk. So let me pause here for a few seconds and ask Ziv, are there any questions?
So if I could jump in there, please, Harsha. You've sort of immediately gone to an infinite mixture model after noting the complexity. Why? As opposed to sort of stopping with something a lot simpler?
So I'll point that out in a second. Okay. So that's literally the next slide. Yeah. Okay, so
Fernando, did you have a question? Okay, sorry, go ahead.
Okay. All right, so let's talk about the methodology. And let me address Shane's question immediately. So, simple models are always good in the sense that you can maybe say more about these models statistically and probabilistically. And in relation to thinking about these types of Cox models or doubly stochastic models, this paper by Brown et al. Is, in a sense, a classic, and it's sort of exemplary of the existing methodology that our community has studied for these types of estimation problems. And broadly speaking, the setting in this paper is you have data that consists of count arrivals over multiple days. And in this paper, they discretize time, and they then also assume a discrete time series model of the underlying intensity process. And they propose maximum likelihood and least squares estimators for the underlying intensity model. So let me make this a little bit more precise. So that I call this as a time bin model. So what they do is you have multiple days of data, as I pointed out. Implicitly, there is an assumption that the stochastic process generating each day's data is independent of the other days. They then divide each day into uniformly binned time intervals. So lambda 1 through lambda n. And then you look at the counts of the number of calls or whatever in each of these time intervals. So each row represents a day. The columns represent the time of the day. And you sort of formulate this massive arrival count matrix. And one of the assumptions here is that these Nijs in each of these bins is generated by a Poisson probability measure that has some unknown intensity lambda ij. So in day I and bin j, you have an intensity of lambda ij. And of course, this is the reason why it's a Cox model. And implicitly underneath that is a sort of rate matrix, if you like, that's associated with these counts. So in each of these bins, there is a corresponding rate, lambda ij, that's modeled as a random daily effects model, where Ri is a random daily effect that you don't know. You try to estimate that. Tau j is the fraction of calls that you estimate will occur in interval j or in bin j. And epsilon ij are given random errors that are known to you. So you've sort of formulated this time series model of the rate or the intensity. And this type of time binned estimation model, I won't get into the specific results in this paper, but at a high level, I would say, and this is directly related to Shane's question, it's really good. Like these types of models are really great because they allow you to use finite dimensional maximum likelihood estimation, and we can say a lot about finite dimensional maximum likelihood estimation. Asymptotics, consistency, central limit theorems. So population level inference is something that we understand really well. But I argue that there is a problem in doing this. Namely, it sort of commits estimation of this rate or intensity to a single timescale by locking the intensity to the count timescale. So we are saying that we are observing arrivals at a specific timescale. And then we're saying that the underlying intensity should also be estimated at the same timescale. But there's actually a lot of fine structure in the trace data that's completely lost by doing this. The underlying intensity could be fluctuating at multiple timescales, which you completely lose if you don't explicitly model them. There's also an assumption of independence across days that is crucial for the statistical inference that this paper advocates for. But nonetheless, that's not so important. I would say it's the loss of this fine structure that's really, really problematic. And in fact, Brown et al. In the same paper sort of acknowledge this upfront. So they say that a natural suggestion would be to use some kind of a non-parametric model. But they also point out that they, at that point in time, which is now 20 years ago, had not actually succeeded in producing a statistical methodology that could actually do this with reasonable theoretical guarantees. So in this talk, I want to sort of try and address this question. So how do we estimate this intensity function without binning it in the same way that, or tying the binning to the count timescale? And also, can we get away without binning at all? So in other words, can we do something that's a little bit more non-parametric? And in a sense, the problem that we're trying to solve is sort of a inverse problem. And here, there is a guiding principle that I like to quote from Andrew Stewart in his book on inverse problems. And he has this Bayesian approach to it. And he says in this book, it's like a monograph, that you want to avoid discretization until the last possible moment. Of course, what is the last possible moment? That's a question open to interpretation, but you don't want to a priori discretize and then sort of commit yourself to a fixed timescale. That seems to be a major issue with how we've been approaching this problem. And with this in mind, we have to then sort of dig a little bit deeper into our specific estimation problem. And consequently, we'll see that actually we don't want to live only with simple finite dimensional models. We actually want to embrace some kind of non-parametricity, and we want to work with infinite dimensional or infinite mixture models. And hopefully I can convince you that this is a good way to go. So to move beyond bin models, let's look a bit closer at our estimation problem. So fundamentally, what we're trying to solve is a non-parametric maximum likelihood estimation problem. NP, because the maximum likelihood problem that we're trying to solve involves maximizing over measures on, an infinite mixture. And these measures are infinitely supported, or they're not just, finite mixtures. And the objective that we would want to maximize is basically the log evidence of our model. So this thing here is typically called as the evidence. And the expectation that we're taking is over the data generating measure. So assuming that we had access to the data generating measure, this is the problem that we are actually trying to solve. Of course, we don't actually have access to this data generating measure. So instead, what we tend to use is a sample average. So we have samples drawn from this data generating measure, and we will solve the sample average problem. Okay, so if we assume for a second that this evidence model has some niceness to it, in the sense that if the class of models that we're using are somehow either parameterized by a small number of parameters, or they're over a finite dimensional domain, so they're somehow supported on a finite dimensional subset of the overall domain. In theory, expectation maximization is exactly how we should approach this problem. We should try to solve this problem by, solve the MLE problem by just doing expectation maximization. So a theoretical expectation maximization iteration here would involve, iterating these two steps. So you first compute an expectation of the log likelihood with respect to your current estimate of the posterior. So posterior over your latent mixing variable, given your observations and your current estimate of the parameters. And then you greedily maximize this expectation to produce a better parameter. And then you iterate this. And you iterate this procedure until you converge. And it is provable that if this class M is nice, in other words, it's finite dimensional, or there's a finite support and so on, this procedure will converge to the maximum likelihood estimator, theta star. Let's call it as theta star. So what's the problem? Well, even if we stick with this assumption that script M is simple, in general, this posterior measure is incredibly hard to compute. I would argue it's impossible in most cases. And in fact, this is something that people in the statistical literature have acknowledged. And it's a well-recognized problem. In fact, there is this classic monograph by Bruce Lindsay on mixture models, where, Bruce Lindsay is actually I think he was the first person who introduced expectation maximization to solve, mixture model estimation. And he sort of points out that, okay, you can use EM, provided that you have the patience for a very slow algorithm, but more problematic, you also need to monitor the gradient function. And in general, this is really hard, like just, making sure that the gradient is converging is an incredibly hard problem. And the part of the reason why it's really hard is because you can't get this posterior and you're trying to update the posterior. And the reason you can't get the posterior is you don't actually, you're not able to actually compute this integral down here. So in general, this log evidence computation is just intractable. And it's intractable even in finite dimension, and even if you're assuming that it's a Cox process and so on. So this is a very classical perspective of trying to use expectation maximization to solve this problem. But a more modern approach, one that's been used in machine learning quite extensively, is to approach this intractability by using some kind of approximation to this objective. And you get approximations to the objective, but also to the gradients involved. And this type of approximation is called as a variational approximation. So let me sketch this out a little bit. So recall that given our evidence, P mu, so mu is our mixing measure, and we have our likelihood P of X given lambda, and then the true posterior is going to look something like this. Instead of trying to directly compute this posterior measure, I'm going to introduce an approximating class of probability measures, conditional probability measures that are absolutely continuous with respect to my prior or mixing measure mu. Okay. And I'm going to assume that such a family exists. And the whole effort in today's talk is to show you how to construct such a family in a sense. And I'm going to introduce a lower bound to my log evidence. This is called as the evidence lower bound. And the way I'll do that is to just subtract the KL divergence between a measure in this approximating family and the true posterior. And this Kullback-Leibler divergence, of course, is non-negative. And so therefore, this log evidence minus the Kullback-Leibler divergence is necessarily a lower bound on the log evidence itself. A little bit of algebraic manipulation brings it into this particular form. And these terms have names. So this specific form, this term is called as the reconstruction error. My iPad is falling off, so I'm not able to write this too neatly. Okay, reconstruction error. And this is known as the prior bias. And as we go along, it'll become clear why this thing is called as a reconstruction error. And this prior bias is because we're trying to make sure that our approximate posterior tries to match some features or some behavior of our mixing measure. Or you can also think of this as a prior measure. This object is called as the elbow, and I'm going to call it as script L as we go along. And if you notice, this is actually a tight lower bound on this log evidence, because if my approximating posterior family actually included the true posterior, then this KL divergence is necessarily 0, and therefore this becomes tight, right? So this is a tight lower bound on our log evidence. And therefore, we actually get a tight variational approximation of our overall objective, which was this maximum likelihood objective. And we have this tight lower bound on this optimization here. Now, this is good because this evidence actually doesn't require me, this elbow rather, doesn't actually require me to compute the posterior anymore. I can just search through this class of approximating posterior measures and then compute the this elbow and then optimize the elbow. But if you look closely enough, there is a problem in here. And the problem is that there is a per sample optimization over here. So for every sample point X that's drawn from the data generating measure, I actually have to maximize this elbow and then maximize over this class of measures mu, or these models mu. And this is a real massive problem. Like you can't actually do this per sample optimization at all. Like this is not feasible. So I don't want to do this. And what I would really like to do is somehow move this maximization, this per sample maximization, outside this integral. And the question is, how do you do this? And in fact, this is a problem that was confronted in deep learning roughly about a decade ago. And they came up with something called as amortized variational approximation. And the idea in amortized variational approximation is to avoid that per sample elbow optimization by parameterizing these conditional measures by a neural network. So you say that somehow there is a neural network that's parameterized that will map my my data samples to some parameters corresponding to this conditional measure. So these could be like the mean or the covariance, for instance. If these measures were Gaussian, then that's all that I need to estimate. I just need to estimate like a conditional mean and a conditional covariance as a function of my data. And assuming that we can do this, I haven't told you how to do it yet. Assuming that we can do this, then we can approximate the NPMLE objective, our maximum likelihood estimation objective, by instead of maximizing over the measure for each x, I'm going to maximize over the parameters of the corresponding neural network. Of course, this entails a further relaxation of this inequality, right? So this is with loss of generality. So the moment you introduce this neural network, you've sort of widened this gap. And this gap actually has a name. It's called as the amortization gap. The amortization gap. And one of the open questions in this generative modeling literature and deep learning literature is how to quantify this amortization gap. And there are really no good answers, even in simple finite dimensional settings, to this question yet. In fact, I just wrote a proposal with a couple of statistician colleagues aimed at sort of understanding this amortization gap. Okay, so I don't know if I can, yeah. So the question now is, if I've convinced you that using amortization and variational approximation is a good thing, then how do we do this on path measures? So far, I actually have not introduced any models, right? This is purely probabilistic in nature. So now I need to sort of tell you what class of models am I going to talk about in this context? Okay, so actually, maybe I can pause here and see if there are any questions. Okay. So let's talk about the types of models that I want to use. So I'm going to assume that this class of mixing measures or models, script M, are path measures that are induced by non-negative stochastic differential equations whose drift is modeled by some universal function approximator, like a neural network, for instance. And these types of objects are usually called as neural SDEs. And one example would be something like this. So you say that my intensity variable lambda is modeled as this SDE, where this drift function alone is modeled as a neural network, and I give you a fixed structure for the diffusion coefficient. The positivity of this solution is typically guaranteed by imposing some constraints on the neural network, but also the fact that we have a square root diffusion coefficient here. And each of these parameterized neural networks, each of these parameterized neural SDEs will induce a specific path measure in this class M theta. And this is only one architecture that one can use. So this is a specific choice that I'm going to make. And I'm going to maintain this choice through the remainder of this talk, simply because we can hang a hat on this. But the methodology itself is not tied to this assumption. But it just helps to fix this right now. And you can ask why a square root process. And one reason why is in this paper by Jiheng, Jeff, and Xiaowei, they actually argue that the Cox-Ingersoll-Ross model where this drift function has a specific structure and you have a square root diffusion coefficient, is actually a really good model for the call center data that I showed you earlier. And this is a really nice paper that's worth taking a look at. Okay, so this is about that class of mixing measures script time. What about the posterior? So to actually define the class of approximating posterior measures, we need to delve a little bit into stochastic filtering theory, specifically stochastic smoothing. So let's say that I have my data sample paths are like these count sample paths. Okay, so I'm looking at counts over time, and that's this blue curve over here. And let's say that the intensity path is sort of sinusoidal with like some Brownian fluctuation on top of it. And what I'm interested in perhaps is to look at, okay, what is the conditional probability that the underlying intensity will take a specific value delta, given that I see an entire sample path of counts from 0 to capital T. So I'm looking at the marginal density, marginal conditional density at a fixed time t of the underlying unobserved mixing or intensity process cap lambda, given this observed sample path from 0 to capital T. So this type of problem is called as a smoothing estimation problem. And when you have Poisson, if you assume that that it's really a Cox process that you're looking at, there's been extensive study of this in the control or stochastic filtering literature. And there's this paper by Malcolm and Elliott from 2005, where they derived the smoothing posterior density. And they show that this smoothing posterior density corresponds to a specific diffusion process. And that specific diffusion process has the same diffusion coefficient as our mixing measures that I showed you in the previous slide. And it has a drift function that has the following structure. Now, this drift function includes the drift from our mixing class of models, as well as a function that basically includes all of the path information of the observed counts that I have, right? This count path that I have that's sitting inside of this part of the drift function. Now, I'll talk about this in a moment, but notice that these stochastic processes, these diffusions, now induce measures that are in this approximating class of path measures. And these path measures are actually all equivalent to the measures in my class of mixing measures. Okay, so this is exactly what we wanted to construct in order to solve our NPMLE problem. So it turns out that this drift function here, so if I just go back for a second, oops. So this drift function actually, in fact, this function here in the drift is not available directly. You actually have to solve a parabolic PDE to get that drift function. And this involves solving this parabolic PDE for this score function. Now, this score function turns out to be really hard to compute for. In fact, it is mostly intractable in practically every case that I've seen. And so if you have to solve a PDE to actually solve for the class of approximating measures, then this becomes a really challenging problem. So instead of trying to solve this PDE, what we end up doing is to, in essence, replace the score function by a neural network. So instead of explicitly solving this PDE, we will introduce a neural network that we train to match the solution of this parabolic PDE. So in the process of maximizing our log likelihood problem, we will also train this neural network to obtain like the solution of the score function. Since we are trying to approximate the score function, I call this as a score matched smoothing posterior. And so using this score matching, we can now optimize this lower bound problem. So we maximize over all possible mixing measures and all possible approximating posterior measures. this elbow functional over the data generating measure. And this specific thing that I've highlighted in red is basically what we get for the elbow function in this setting. Okay, so the it turns out that because we're using diffusion models, the elbow function actually has a much simpler form, which can be obtained by using Girsanov's theorem. And without getting into the details of Girsanov's theorem, what we can see is that so if I go back here, so this likelihood ratio here, this log likelihood ratio, can be expressed in terms of the drift functions. And it turns out that we'll get this specific form here. So this function u depends on the drift function from the approximating posterior and the drift function from the mixing model B. And this gives us our final form for the score-matched NPMLE objective, which looks like this. Of course, as I pointed out before, we don't have access to this ground truth measure. And instead, what we will actually maximize is this sample average or empirical average, where we obtain samples from this. We have a data set that's sampled from this ground truth measure. So this is our final objective that we are going to maximize. So before I sort of illustrate this methodology, I should point out that this method can also be viewed as a variational autoencoder. So variational autoencoders were developed in the deep generative modeling literature for image generation. So the idea there is, you have many samples, data samples that correspond to faces, or the images of faces, for example. And there is some latent structure, something that defines what a face is. And you try to learn that latent structure by encoding each image into this latent space. And this is done by training a neural network to estimate the mean and the covariance of a Gaussian, a conditional Gaussian probability distribution. And then this is called as encoding. And then to generate new images, you learn how to decode. So you sample from this latent space according to some fixed probability distribution. And then you learn how to decode back to the data space by estimating another conditional Gaussian distribution. And in the decoder direction, you are trying to learn like the mean and the covariance again. But these are two different neural networks. I'm sorry, so the mu phi and mu theta are two different neural networks, similarly sigma theta and sigma phi. The training procedure, however, couples both mu phi and, well, these neural networks, these phi parameterized neural networks and these theta parameterized neural networks. This architecture is actually very much analogous to what we are doing in the NPMLE setting. And if we wanted to frame the NPMLE problem in this variational autoencoder terminology, what we're trying to do essentially is to learn the infinitesimal mean and variance of a latent intensity model. And then we're also learning how to decode through a Poisson kernel. And so, you can see that there's sort of an analogy between variational autoencoders and this NPMLE problem that we're trying to solve. I'm happy to talk about this more later on, but let me get to some of the numerics that will illustrate what we can do with this methodology. Okay, so just to recall, what we're trying to maximize is this empirical average objective. And we're going to maximize over neural networks parameterized by theta and neural networks parameterized by phi. And the way we'll do this is to use batched stochastic gradient descent. And notice that one of the neural networks, there's actually a coupling that we create between the approximating posterior neural network and the mixing model neural network through this function u. But what we'll end up doing is sort of introduce another approximation purely for numerical reasons and sort of decouple this u from the theta neural network. So we'll just create two separate neural networks, one parameterized by beta and another one parameterized by theta. This is purely for numerical reasons, but it does entail a bit of loss of generality. And there are some further errors that are introduced. But again, I don't really have a quantification of how bad this mean field approximation can be. So this is an important open problem. Now, to use stochastic gradient descent to train these neural networks, U beta and B theta, we have to somehow propagate gradients backwards through time on a path-by-path basis. And the way we do that is to compute a Jacobian STE and then essentially simulate this Jacobian STE itself. This Jacobian STE will be used in our training problem. So if we go back to the objective, notice that we have to simulate this approximating diffusion, this approximating posterior diffusion for every given sample path n. And that will go into this computation of the gradient stochastic process. Okay, so this is a bit dense. So let me just get to the numerics. Here's the overall architecture for these experiments. For the B neural network, so the theta parameterized neural network. So this is the mixing model. So this is the mixing model, and this is the approximate posterior. In both of these cases, we just chose fully connected 7-layer neural networks with these number of nodes in each of the layers. Why did we make these choices? This is totally arbitrary. I honestly don't have good reasons for using this. You could use other things and get equally good or equally bad results depending on your opinion of what you're about to see. Okay, so if I look at one simulation experiment where we say that the true model is a Cox process, okay, with diffusion intensity that looks something like this, with these parameters. I'm starting at level 5, and I have a long-term average of 80 and a relaxation parameter of 0.3. Then the log likelihood changes according to this the blue curve here. And the elbow maximization, as you can see, sort of quickly tracks the log likelihood. So the amortization gap is somehow small, and the elbow gap is small in this example. It looks as if they are exactly on top of each other, but they're not. There's still like a positive gap between them, but you can't see it at this scale. And once you've run this for about 100 epochs of the stochastic gradient algorithm, this is what you see. You see this. So these blue curves here are what you get from the training. And each of these paths is one of the approximating, is a sample path drawn from the estimated mixing model. And this corresponds to some B theta drift function. And so we also have like a small video that shows how this training evolves over time. So I'm just going to speed it up a little bit. So as you see, as the number of epochs increases, so at every epoch, we're sort of generating about 128 sample paths to train this method, this algorithm. And very quickly, you sort of see that it stabilizes. And it looks, and those gray sample paths in the background are basically the sort of the true data generating sample paths. So it sort of stabilizes very close to the true model in this case. And you see something similar if you introduce time dependencies in these drift functions. So we're not just looking at stationary models, but also models that have some kind of time non-stationarity in them in the drift function. Again, you can sort of see that the elbow estimation is pretty tight, and the elbow approximation rather is pretty tight, and the learned drift looks pretty accurate in this case. So this is all for simulated data. Let me skip that. If we look at actual call center data, where we don't actually have, we don't really know what the data generating model now is, we can still see that this method does pretty well. So we do a bit of data pre-processing. So in this particular example, these sample paths correspond to all the Fridays in the data set. And I'm looking at counts over a 1-hour time scale. And so if you think back to the data matrix that I showed you way early on in the talk, this would be like, that uniform binning that was done on the observations is at the 1 hour time scale. And there are approximately 130 sample paths in this data set. And we do some minor tricks for numerical stability, neither of which really have any impact on the final estimated model. So after you train, what you see is the following. So the trained model has, you sort of pick up the diurnal behavior, but you also have like these fluctuations at, a certain time scale that's determined by the diffusion coefficient. And here's like a video of how this algorithm learns. So if I just speed it up a bit, you can see that it takes a long time. So now we need about 170 epochs for it to converge. And around about 100 epochs, you start seeing like the diurnal behavior, it really picks it up and it kind of latches onto the overall underlying structure, what it thinks is the intensity. Okay, so this is with one of those tricks called as gradient clipping. So essentially, the stochastic gradients can become quite unstable. So we sort of rescale the gradients to below a certain norm threshold. And if we do it using that gradient clipping, then there's a bit more elbow error. The approximation isn't as tight, but we do get a slightly better variance, I would say, behavior. But there's a lot of overfitting early on in this data set. And again, these methods are very, very sensitive to hyperparameters. So if I wouldn't claim that that's what we always see. If you make good choices on these hyperparameters, you might see something like this that looks really good. But this is like a best run, and you don't always get this, so it's very sensitive to those choices. But the important point is the following. So you actually pick up the diurnal behavior. You see the time of day effect. And these simulations are being done at a much finer time scale than the count time scale. So remember, the counts were at every hour of the day. And these simulations were of the intensity process were at like 15-minute time scale. But you can do it at even finer time scales. Okay, so I think I'm out of time, essentially. I'll just make one last point. So it's not just, so these are all like in-sample simulation exercises. You can also do data generation exercises. So here's an example where we held out 20% of the sample paths in the data set for testing. And then we trained on the remaining 80% of the data sets. And the blue curves here sort of show the data that was generated, fake data. So it was the fake sample paths generated from our model. And the red curves are the sample paths from the held out data set. So one thing that should, two things should stand out. One is we pick up the time of day effect, as I pointed out, but also notice that we have much lower variation across these sample paths. And the reason why this is happening, I think, is because we have fixed the diffusion coefficient. And our methodology is not tied to a fixed diffusion coefficient. We can also learn the diffusion coefficient. We haven't done this, but if we did it, my conjecture is that we would actually learn this really well. So let me pause here and ask Ziv, should I stop or for
I'd
questions?
say,
Or
if you have like a conclusion, you can spend another couple minutes concluding, and then we'll take a few questions.
Okay, excellent. So let me skip straight ahead. So there's probably too much in here. I think I should. Okay, so let me just talk about some of the open questions that I have for the score-matched NPMLE methodology. I didn't talk about guarantees, but what we have right now are sort of probabilistic guarantees on this method. By probabilistic guarantees, I mean, okay, so we've learned a model of the mixing measure, and if we we can sort of show that, yeah, we can actually generate samples that are very close to the true data generating measure. We can prove this, provided that our neural networks are powerful enough. We have enough capacity in our neural networks. But we know nothing about statistical guarantees for this method. So if we are in a finite sample setting, what can we say? And this is totally an open problem, not just for this core-matched NPMLE, but also for variational autoencoders and deep generative modeling in general. And one of the methods, maybe statistical methods to answer this question, might be through M estimation theory. Maybe that can help. The second question is, a lot of the experimentation that we've done so far has been focused on Cox processes. The methodology is not tied to Cox processes, but Cox processes automatically give us like a Poisson kernel. How do we move beyond like Poisson kernels? Like if we were to describe general point process kernels, can we still use this methodology, and how would that look? Can we extend this to queuing networks? So this whole talk started with this motivation from complex stochastic networks. There's nothing stochastic network yet in any of this. But how do we use this methodology to learn queuing networks and queuing network structures, including routing and flows? And I think we have to somehow embed the flow structure into the latent space. And this is like a question that we're working on right now. And lastly, if you paid close attention, you would have noticed that I assume that I have multiple sample paths from this data generating distribution. But what happens if I just have one long observation? Is there a way to do like single shot learning of these point process models? And of course, this would kind of assume some kind of stationarity and so on, but that's an important question. And so finally, let me just end with making a connection to causal inference. And I think what we are essentially trying to do when we talk about data-driven stochastic modeling is we're trying to develop an inference engine for stochastic modeling of the type that Judea Pearl sort of proposed for causal modeling. And I think we want to think carefully about this type of question. And this, I think, is an important challenge for our community. So let me end here and take any questions that people have.
Let's thank Harsha for a great talk. And I'll put the link to the slides in the chat once again, so folks can at least take a look at some of the slides that you had to skip through at the end. So are there any questions?
So Harsha, thank you for thank you for the talk and for, I think I've always been puzzled by these diffusion processes you ran backwards and forwards. So this was helpful. Thank you.
Sure.
So I guess I've dabbled a little bit with statistical modeling and how it applies to operations. And what I'm seeing in the work that you're doing is that you've got this very statistical focus, and there's not really necessarily a connection to the operations at the end.
Right.
So how does this change the decisions that you're making for your call center, for example? Have you explored that, and do you see potential there?
Absolutely, yeah. I mean, this ultimately, I think the proof is in the pudding, right? Like we have to use it for decision-making, control, performance analysis, and so on. So one of the experiments that I didn't talk about was like run-through experiments that we've done. And here, what we did is, so let's say that you generate data from a true model whose intensity is like some CIR SDE. And we'll run this data through an infinite server queue. And and then I train this model, right? I solve this NPMLE model, and then I simulate traffic from this learned model, right? So I generate data, and then I run it through the same queue, right? And so I'm going to look at the performance now. I'm going to look at the number of occupied servers, for example. So what kind of predictions do I get from a performance perspective if I'm looking at the number of occupied servers? And so this is one of the experiments that we've done. One of the things that I'm working on with my student right now is, so we have this latent space, right? So decisions, optimization, design, and so on has to happen using our understanding of the intensity model. In other words, the latent space. So can we mine the latent space for better decisions is one of the questions that we're going after. So I completely agree with you. I think I only have like a partial answer to your question through these types of run-through experiments, but it's definitely on my agenda to address this question.
And maybe just a quick follow-up, Ziv, is that okay?
Yeah.
Thank you. You mentioned fairly early on that you were also wanting to explore the fine structure in
Yes.
the processes that you're modeling. I guess one question I would ask is why?
Yeah, because if you look at decision making, like designing a queuing model, just think about the square root staffing rule, right? So the square root staffing rule is premised on, okay, there's extra variability, and how do I deal with it? Now, if I have, and that variability can manifest at different timescales. So when I'm designing like a staffing rule, it doesn't have to be square root staffing rule. Maybe there's a different rule that emerges when you have like, multi-scale structure. So what is that type of rule? And can we infer it from the latent structure that we're learning? That's kind of the vision that I have. That I think that there is something there when we start looking at these hierarchical, multi-scale latent spaces that we're building up. I think we can identify these types of interesting, non-obvious rules to use. Or maybe we'll confirm that, yes, square root staffing is the right thing to do under a large set of circumstances. But I think that this is a tool to sort of do this type of mining, if you like, for new rules and control policies and so on. Does that answer your question?
Yeah, thank you. I think there's multiple paths to getting those simplified rules, those simplified insights, but I see where you're going.
I agree.
Thank you.
Sure.
All right, any further questions? Okay, Harsha, I have one question about about the derivation of the elbow lower bound. So you have so the elbow lower bound involved basically this conditional probability distribution like u given x. And basically I was wondering if there was is there a is there a is there an intuitive interpretation of like what the exact u given x would be? And so that like, because I think I understood that, oh, we're trying to derive a neural network to sort of give the approximate u given x,
Right.
Via this function phi. But I think I couldn't quite figure out what exactly it was that we were approximating, or at
Sure.
least an
Yeah.
intuitive
So
interpretation. Yeah.
yeah. So let's look at the elbow objective, right?
Yeah.
So if we go back to this slide here. So this so this derivation is almost trivial in
Right.
some sense, right? So you end up over here, and so you have this this is this new x here. This is our approximating posterior, right? And this new x, if you just stick it into our NPMLE objective, will sort of necessitate an optimization for every sample path x, right? So you'd have to do this like per sample path optimization, and then average over that, and then maximize over all the models. Okay, so what we are doing next is to sort of say, okay, I don't want to do this per sample path optimization, but I'm instead going to say that, okay, there's a neural network that parameterizes this measure in some way. I don't know how yet. And then I'm optimizing over the parameters of this neural network that isn't like specific to each sample path. So then I can, in theory, sort of move this maximization outside the expectation. And then the question is, okay, what do you mean by this? Like, okay, in theory, this all sounds very plausible. But the way that we do it is to like construct this path measure through this diffusion, et cetera, et cetera.
Sure. So I think the thing that I was missing, or perhaps missed, was that the thing we are approximating is this posterior measure.
It is the posterior measure.
Okay.
Yeah.
That makes sense.
It's the posterior measure. And in fact, that's this. So the measure corresponding to this stochastic process is an approximation to an approximation in a sense. Like there's two levels of approximation that are going on to get this whole thing to work. Yeah. Which, given all of these, various approximations, it is still a bit amazing to me that, you can kind of capture, a lot of the features that you want to capture with this methodology. And we are able to prove that, okay, if you have enough capacity in these neural networks, you can actually, get really accurate results. I think that's, it's amazing that you can do this. Yeah.
Exciting.
Yeah.
Okay, thanks. Any last questions? Okay, well, with that, we'll conclude Snap. So thanks for coming, everybody. Snap will return in 2 weeks on April 14th. So hope to see you there.